thank you everyone for showing up for this talk or for remaining after such a long morning. Okay, so I was told this is a colloquium style talk about number theory. So I guess my aim will just be to give you a sense what elliptic curves are and what kind of arithmetic questions we can ask about them. So the main theme that should appear, hopefully, throughout my talk is how the constraints that we put in our objects somehow make many structures coexist at the same time, and how the interaction of the different structure provides us with interesting questions that, I mean, most of them we don't know how to answer yet. All right, so let's begin to look at what elliptic curves are from different points, from different branches of mathematics, and we'll begin with topology. So we have seen some of these pictures in Irene's talk. So in a way, you can think about my talk as somehow the exercise session. I'll focus on genus 1, dimension 1, and everything. So everything should be more accessible. I will draw more pictures. I'll write down more formulas. So hopefully something will remain between our two talks. Okay, so let's begin with topology. So we want to build our elliptic curve. And as we've seen, we can just take a piece of paper, this form, we glue two sides together. This side, we get a cylinder. And if we glue the other two sides together, we get this, what is called a torus or inflatable donut. So something like this is usually pictured in this way. And there is one loop that goes around the whole in the air and one in the middle. All right. So here we're really, if you want to do more math, you can think of this as some subset of R2. So it has some topology. So this is some topological manifold. And there is this nice, the first example of this phenomenon I mentioned before, this feature that since the dimension is small, in this case, less or equal than 3, there is any topological manifold as a unique differentiable structure. So either if we choose to think about these donuts up to homeomorphisms or diffeomorphisms, there is only one. So in other words, this is the orientable surface of genus 1. And the genus, as Irene said, is just the number of central holes in the donut. All right, so and again, let me stress this point once more. It really depends what kind of isomorphisms in your category you're considering. So up to which equivalence relation you're considering your shapes. So this is a very strong equivalence relation. We allow many, many maps. And so we get a unique object, in a sense, in this space. All right, so it's the beginning, not super interesting, maybe. So let's start to add structure to it. Maybe we'll get something more. Okay, so this was topology. Let's start to do some geometry. So Euclid or the Egyptians told us that geometry should be the study of lengths, angles, and well, in this case, we'll just care about. So we have our, again, let me write it here. So our space is this donut S. And we want to have a way of talking about way to measure angles on this space. So this structure is called a conformal structure on S. So I'm just going to write down the names. For I guess the more mathematically minded, this should be some Riemannian metric up to scaling by smooth functions. So it gives just a way of measuring angles on tangent spaces. But again, because the space is so constrained, conformal structures, in this case, are the same as, well, here we can measure angles. In a two-dimensional space is actually enough to be able to rotate by 90 degrees. So in this case, being able to rotate by 90 degrees is what is called a almost complex structure. right? So again, in mathematical terms, this is some endomorphism of the tangent bundle whose square is -1. So if you think about the complex plane or R2, multiplication by I is just rotation by 90 degrees. All right, so in general, if you've seen any course in differential geometry or complex geometry, not every almost complex structure comes from a complex structure on the space. Or as we have seen in Irene's talk, we can cover the space by patches, which looks like C. But again, because the space is so small, so constrained, in this case, there's no obstruction, and any almost complex structure is the same thing as a complex structure. Okay, same thing. Okay, so we start from wanting to be able to measure angles, which we do, rotation by 90 degrees. And well, I don't have a nice elementary way to describe this, but somehow locally our space looks like the complex numbers. All right, so why did I go through this? Well, now we can start to think how many different complex structures, a conformal structure, almost complex structure can we put on S? And the advantage of working on the complex side is that now we have, I hope you can see if I write here. So this is called Riemann's uniformization theorem. Which implies that if we take S and we choose any such a structure, this structure will look like this. We take the complex numbers and we mod out by a lattice, which will depend on tau. So lambda tau will be our lattice given by the integers plus z tau. I will soon draw a picture, and this tau is a complex number with positive imaginary part. So the picture here looks like this. We have the complex numbers. So this is C. We have the element 1, for example, and the element tau that could be something here, right? So we need to form our rectangle as the beginning. So in this case, it looks like this. And then doing, this formal operation of quotienting out really says that we are translating everything in the plane to land inside here. And of course, we identify sides as before to form our donut. But now we just don't take any piece of paper, but really it's important which tau we are considering here. Because that remembers this extra geometric structure. Okay, so now so this allows us to say how many different such structure we can consider, because we have found that, so there is this map, so H, so I remind you, these are, I guess, the elements in C with imaginary part positive. In the space of those objects, we already were giving a name. These are complex tori of dimension 1. So this map takes a tau here and produces the torus C modulo lambda tau. So this map, from what I just told you, is surjective. So any such complex torus can be written in this form. But the notion of equivalence in this category is, are not just any homeomorphism or any diffeomorphism, as in the topological case. We require the maps to be holomorphic or biholomorphic. So we need also to mod out here by the action of a group, SL2Z, which acts by Möbius transformation. All right, so now in this way, this becomes a bijection. And the upshot, I guess, is that for geometers, there are well, this many, which you can think of as a sphere minus 1 point, complex tori of dimension 1. All right. So you can think of as any point on the sphere like parameterizes a different way of measuring angles on your donut. It's maybe I can do this. All right. All right. So what have we learned? Now, by adding extra structure, we gain, we entered the world of complex geometry. We saw that these objects are Lie groups. So as Irene said, we can add points on them, and this operation makes sense. But we want to do, or at least I want to do number theory. So I need to make sense of the rationals. So the rationals, when you do analysis, don't behave very well. So, we need some polynomial equation to show up at some point. All right, so now I can probably fill right to this side. You can see. And now there is another surprising fact, once more, because of the constraints of the situation. Is that complex tori of dimension 1 are the same thing as, well, as I said, we want to study object given by polynomials. So it would be something like algebraic curves of genus 1 over C. But it's not quite there. Like, we need to add some adjectives that are not super important. So it's projective and smooth. So smooth, saying like, as this is a manifold, it doesn't have singularities in the same way our curve shouldn't have those singularities, right? And let me stress, this is a very special thing that happens only in this case. So if, for example, if you look at tori of higher dimensions, they're not all algebraic. And another thing is that the nice feature is everything being so simple, I can even tell you how to see this thing, which is very cool. It's something, Weierstrass and Poincaré studied in the 1800s. And so how do? You produce enough meromorphic functions on these torus, and you show that they satisfy a cubic relation. So I can write down the function for you. So say you have your favorite torus, C modulo lambda tau. I can write Weierstrass P function. So it's a function on the complex plane. It should be a function with a pole at some point, and which is translation invariant by the elements of this lattice. So we want a pole at 0. All right. We put a double pole here. And then to make it translation invariant, I just sum over the element of the lattice. But maybe I remove the 0 element because I consider it separately. And to have, so the natural thing to do would be to sum these terms, but this doesn't quite converge. So you need to modify it slightly. So this way you get something which is uniformly convergent on compacts, converges to some holomorphic function, meromorphic functions with poles only on the lattice, and so gives you a meromorphic function on your favorite torus, which has a double pole at infinity. So, one thing we could do is we could consider its derivative. So we derive with respect to z, right? So if this had a double pole, this will have a triple pole. And now you can try to cancel the pole by multiplying these two things together. And it turns out that if you call this x and this thing y, they satisfy. So they satisfy. the following cubic equation. So y squared equals 4x cubed minus something that is usually denoted by G2 tau, so some constant that depends on tau, x minus G3 of tau. Okay, very nice. So like that's somehow how this relation comes about. So you have your complex torus, and you associate to it the equation, well, 4x cubed minus G2x minus G3. All right, so we are in very good shape now. We have an equation. These coefficients are complex number in general, but if we want to do number theory, we can, force them to be rational numbers. So I'm finally ready to give you the definition. And so let's go to number theory. So for us, an elliptic curve E is just an object described by an equation of this shape. And let's say we want to do arithmetic over the rationals. So I'm going to take the coefficients to be in Q. And then I need to ask for some relation between A and B so that my curve will be smooth. And so the relation requires this cubic polynomial to have distinct roots. And this can be written down in a formula that I always get wrong, but I think it should be something of this form. So it's 4a cubed plus 27b squared is non-zero. All right. So you see, like, it's not very different. But what I want to stress now is that, again, somehow we change category in a sense. So the notion of equivalence between the object has changed. So let me remind you again, in topology, we were considering homeomorphisms or diffeomorphisms. Now in geometry, we have these biholomorphic maps that preserves this extra structure. Well, now we're finally in number theory, and we want to constrain even more the kind of equivalences that we consider. So in a sense, we get more and more objects when we constrains the isomorphism. So maybe the remark is that if now, for example, if I take D not a square, so think, for example, 3 or 5 or 10, like these kind of numbers that are not squares in the rationals, then I can consider two elliptic curves. So this one. And a similar one, which I'll write in this shape. So I just multiply by D the Y. So this equation can be put in the same form as this one, but it's easier to write down this way. And my claim is that these two things are not isomorphic as elliptic curves over Q. So they, the equations are so simple that you can probably guess how to relate the two, right? If I take a solution x0, y0, and I map it to x0, y0 divided by the square root of D, you can see that this is bijective, right? It's given by polynomial equation. So it's an isomorphism, if you want, defined over the complex numbers. So these two things, from the point of view of geometry, are the same. But because we are choosing a square root of D, we're somehow leaving the realm of the rationals. We're adding a square root. So yeah, we have many more to consider. These objects will have the same geometry, but different arithmetic. Okay. All right, so I'm ready to finally just mention what kind of question we can ask about these objects. And to do that, let me remind you what we learned. So if we look at I'm going to denote by these the pairs of x and y's over the complex numbers that satisfy the equation of the elliptic curve. Because of what we saw before, this is the same as C modulo lambda tau for some tau. So there is a group structure. right? So we can add points together. And the very special thing that happens when your coefficients are rational is that the set of rational solution is a subgroup. So the group structure, which a priori, it's completely analytic, if you want, because of all this coexistence of different point of view of structures, preserve rational solution. So if you have two rational solutions, x and y's, that satisfy the equation, you can somehow sum them to obtain a new one. And now the questions that appear, that are natural to ask. So the first one is, for example, how big is EQ? Of course, if let me stress that it's important that Q is, such a arithmetic field, while the complex number are, algebraically closed. So like their behavior will be very different. So how big is this? Well, one of the first results in this direction is due to Mordell in 1922, who proved that this group is finally generated. Which means that you just need finally many solutions to obtain all the others by this operation. Okay, so now you have finally many solutions. There are two kinds of solution you can consider. Those that are non-torsion and those that their multiples eventually become zero. And so regarding the torsion part, I guess Mazur, for example, in 1977, described completely torsion part. And when I say describe it, I mean that it really listed all the 15 possibilities of torsion subgroups of this kind of Mordell groups. And yeah, that's more or less what it did. And then now the last question remaining is what about the infinite part? So very informally, so the open question is that how infinite can EQ be? So for, I guess, the algebraically minded, I'm really thinking about the rank of this finally generated abelian group. And there are lots of open questions about understanding how infinite this can be. And the one I usually think about in my work is related to what is called the Birch and Smeaton-Dyer conjecture, which predicts that it's possible to understand the rank of this Mordell group by doing some analysis. So once more, because of the constraint of the situation, different parts of mathematics come together and provide us with very interesting questions. I'll stop here.